Hello everyone, my name is Ritesh Manhar and I am here to introduce my team Nikesh Arora.
Hello, I am Harish Narwariya.
I am Amrit Raj.
I am Keerthi.
I am Kiran.
I am Pratham Agarwal.
And we are here to discuss our topic, the future of computing.
Good afternoon, everyone. Welcome to the last keynote of Think. I'm really thank you for being here. Some of you glass in hand, as it should be right. My name is Ayan Asario, and I led our mathematics of computation group. And I'll say doing research at IBM is really an incredible job, and we have experts in high precision computing, AI in quantum computing, in hybrid cloud that all come together across labs all over the world. Although the disciplines and science are abroad, we are all united by a common purpose, that's being the organic growth of engine of the company and invent what next in computing. So computing, I want you to think about the role of computing in our lives, because once we turned computers on, we have never turned them off. So think about it. It's pretty remarkable. And not only that, but we rely on them more and more. Our modern world was built on the back of bits, that underlying unit of information powering high precision computing, and we kept building ever more powerful machines and forms of computing with different flavors. We have seen the rise and AI and LLMs that seems to be refashioning our world in real time. And the latest addition to the computing family that came from the fundamental rethinking of the very nature of information, that's quantum computing, where we are hastening quantum mechanics to launch a completely new form of computation. So each of these technologies offer vastly different and powerful capabilities, and at IBM we are not just focused on putting each of them to work, we are actively investigating ways of bringing them together to create new capabilities that are already providing to be valuable. A prime example of that is how we brought the versions of generative AI right into the heart of Jet 17. That's a taste of what's to come, because to uncover the value of these intersections, we formed the Mathematics of Computation group, and the team is working very hard to develop the mathematical frameworks and the advanced logarithms to foster those connections between our high precision computing AI and quantum systems, and to realize their potential to solve those complex mathematical problems that move business. I'm really very proud to be a part of rich history of theory at IBM, where we have used mathematical reasoning pretty extensively in the development of algorithms. And in fact, a few years ago, MIT analyzed the contributions of institutions of the most important families of algorithms, and guess what it found? Look, many people develop their own mythologies and about how science and innovation work, about where the best work is done and by whom, and well, that study showed that IBM has contributed the most and with the most impactful algorithms for science and business. I think we can say that algorithms run our digital world, and IBM has pretty long tradition in the space. And combining our work in this space with our contributions in things like material science in, and that's just an example, because really we have been pushing the computing industry forward for as long as there's been one. But if you ask me, what I find most exciting about my job? Well, there are many things, no doubt, but I think it's that me and my team get to work closely with the top minds leading, researching all of these technologies. I find that very special. And today, in an odyssey of computing scope, I have two of those colleagues that will share with you the extraordinary things that are doing to invent what's next in AI and quantum computing, starting with how we are going to cast off the fetters that are holding LLM captive. And further, please welcome our VP of AI Research, Shreem Ragban.
Good morning, everyone. Always wonderful. Good morning, everyone. It is always wonderful to hear, to think, to share, and perspective on technology with us and parentry. It's such a wonderful opportunity to take about the and computing and here to going to almost independently and products and offering and certain in the world of AI such as chance to you now they really explore to technology and moving it at the terminus and having to continue the research and keynotes involving the shapes and refine and thinking so we let's make it think and down what the about taking about the AI is a keynotes your last 3 years the 30 seconds of and down the memory length. So we have to 2022 we have to first introduce the shape of science and the introductions of the fond of models we take about the technology poses the fundamental challenge to AI getting down and the fundamental change to technology in the landscape it the 2022 again the research and already we about the importance that taking the platform approaching with side AI getting for really notes the thinking across the entire the cycle and consumations of the government the models and then introduce Watson's and X or Watson X and platform U and 2024 began these keynotes and talking about the important data. We said the almost impressive and the resource of the reprise and the truly get the values of AI, the importance of able to get a reprise data and involving so LLM platform. So LLM platform data. So what is the biggest picture in the 2025? You probably expecting the saying the agents, but here reasons for the questions marks and certain the agents we the questions and the engineer and the architecture help to building the entry of the class you knew and the power of applications. But I want to share the today and something so much the fundamentals of fraud of that the wonder way that and something that the beginning to call the generative computing and it is converging. The LLM found the new computing the elements that is coming to in the ecosystem. Yes, interesting to AI effect and we response to represent into the actually the computing elements where is new computing elements and request to time and the working of them and so that we have to motivation you expect and complete the times and tell about the say of the affecting agents actually the pushing on they you and the building of agents today as starting to the LLM the already why do we need to the compliments and so it's motivation to stepping the back little bit of looking that how to try to that industrial in AI the 3 year short terms models that become wonderful and powerful and we started building simplified to cat and we quickly moved that and agents we have to get a complexity and the task we want to get and complexities we have to happen doing the simplified AQ and the summarizations we want to form an an enterprise of workflow and we initially working with the simplified documents and working as multiply documents and speech or sports and we want to other task we want to whether it is data that uh, we want to that how to explore that complex obtain to what is the AI what is to AI the before we super and I'm thinking just what you want to do with AI and it's wonderful here and surprise we have to see in the explore and the framework and protocols. I'm meaning just a something. I could fill the entire chart and icons about the frameworks and appears tools helps in better valuation and connecting tools the agents. The thinking here the frames all the these things of rightfully so because I'm ended to do and applicable this with AI, but you certain step off and back ask to yourself and fundamentally mechanisms and uh, interesting the models of change and no continued and the from the engineering you from that gotten the large and large and even large and every soon I'm going to book and book from that is sustainable. That's my side and thank you.
You can actually see an instance of this agent in the Think forum. The first observation of this is complex, and by the way, this is the simplest prompt. I am not expecting you to read this English, but this is the simplest prompt that you give to an agent. So you will actually recognize this is not maintainable, this is really not maintainable. Let's dig in now to a portion of this prompt. So I am going to look at the portion of the prompt where you instruct your model on the things you want your model to do and you don't want your model to don't do. And I will encourage you to read it, and I will call this security by prayer. You are imploring the model not to do something and not to do it, and this is certainly not a robust way to do enterprise application, and it's open to all sorts of escalations and attacks. Now let's look at the different section of this prompt, of the same prompt, but I am now going to scroll and look at the portion of the prompt where if you read that section in red, you see that it's very carefully crafted. The agent is instructing the model exactly how the output report should be structured, what should be in it and what should not be in it. But what is observing here is this very carefully crafted. Some things are in bold and some things are not in bold. Sometimes you have to tell the model twice that you don't want a conclusion in your report, and this tells you that in the extremely brittle and care model of the AI, it means that there's a very high likelihood, and actually it happens in practice. Then we try to take some agent and apply to a different model. You are going to have to do it that prompt engineering all over again and again to get the accuracy. So the point we are making is we have to expand the ecosystem of models around our world. By the things of interacting with models, we continue to remain using prompt, and the last but not least is a big prompt, like a typically requires a large model to make sense to all type of English languages. So you are now taking a large models of resources. What I am here to tell you that generative computing is the way to move away from prompting to a real programming, is to recognize that LLM is a computing element and to really build enterprise application that are built with different forms of languages like English and all types of languages that are present in the world. The pure prompting and generative prompting. So the thing is that you do prompting with the application of the API through an API model to the model, but you are interacting within the world of tokens. You are on instructing the model thought of the world of tokens. It doesn't matter what the API is, but what's your currency for controlling the model. Now with the world of API, there's a currency for controlling the model. Now with the generating computing here, we have the different forms of API. The runtime exposes of a set of the principal distraction. This is the abstraction for generating computing, and when you expose an abstraction, you now know the much of the structured way to replace the prompt with the something that's actually a realistic way of real programming with your own language, your own mother language. Now I am going to spend some time on the way of using these things and how to use it carefully to become a prompt engineer. So now let's look at the some example that you are wrote in the pages, some pages of English, and ask yourself, you will do it in a generative computing. So I am going to ask you a weaker section of this 3-4 lines of abstraction. We are looking to develop a programming through this simple English language. Now, to a speechless and the security perspective of your model, then there's a notion of requirement where in a very structured way you tell the model what it is, what you want your model to do. And remember, you are not in a simple by writing English that hopefully is correctly integrated. You have to explicit calls that the runtime understands that recruitment. And today here you find an example of requirements on syntax, on language, etc. And the runtime of this enforces and check these constants because it's a piece of software that instructs what your model have to do, and then you put this all together with an abstraction that's called a generative strategy. You instruct the runtime. Are you going to talk to a multiple model multiple times? Are you going to try to different answers and sample? There's a lot to unpack. Now I am going into a detail, but let me give you a brief example of how the thing works in dramatic way. So the first benefit of doing this is that you are going to have and better efficiency. It's a complete example of how thing works in the prompt engineering requires a way bigger model to get acceptable accuracy than by using the generative computing.
Very specifically, that example to get reasonable accuracy that was visible something that requires a 70 billion parameters model with generative computing. We are able to do this with a preview version of a model that uses no more than a billion parameters at inference time. Way more efficient. Second, you have heard me talk about security by prayers. That's not quite the way you want to do enterprise grade. In the world of generative computing, security was a first class citizen. So the runtime will expose abstraction of what you want to do. You want to do check for hallucination, you want to do check for prompt injection, or you want to check for all other kinds of attacks. All these will make changes to your model. You will register an appropriate LoRa adapters that will then implement this in the best of, as opposed to hoping that a piece of paper will get correctly interpreted. You have well-trained adapters that are going to implement security checks, a much more controlled way to do security. And finally, because now you have a runtime, you get portability. Yes, you have to adapt the runtime of different models, but you do not have to change your application code every time because you are not programming to meet the whims and fancies of individual models. You are programming to a structured abstractions. So the takeaway message is that generative computing recognizes that an LLM is a computing devices that you are going to program, which is different from the fact that you can bring natural language application to the user. But when it comes to the computing elements, new abstractions are going to emerge. That's going to make a building agents and applications efficient, secure, portable, and maintainable. And at IBM Research, we are doubling down on this idea of generative computing and involving both our model strategy and the runtime strategy. We are developing a Granite runtime that's going to embody these abstractions, and we are also realizing the next generation of our Granite models that will come out later this. On our models, we are excited that our next generation of our Granite 4 model will come in a number of sizes for something that run on a little GPU on a devices to a model that you can use to the agents and powerful applications. This model exploits a new architecture innovations that combine state-based models which are very efficient with transformer approaches, all packed of a mixture of experts approach. We are estimating with early benchmarks that this is going to have us 2 to 5x advantage over comparable models. So we are very excited that by this direction that we are going isn't very a computing element turning up in our history. That's something like Lexus happened. It's very excited to be able to build new technology and new days of building applications. So hopefully we are able to join us in this journey to make generative computing real for the enterprises. You yesterday, Arvind told that use at AI is moving from experimentation to production, and Rob told us about the billion and more application by 2028. Well, I hope it was clear from Shuron that to make that transition and to get more sophisticated is what we do. And with LLMs, we are really need to move for prompt to programming. And please, whatever you do, please don't do security by prayers. It is really not a good idea to do that. Now, you know, Shuram and his team bringing you maintainable, portable, efficient, secure input computing with LLMs. That's an example of how you are simplifying things to get their essentials and realizing their implication that greater implication for enterprises. Right? We are really making computing edge technology being more performant, more consistent. We are making them more cost effective and flexible. And there's another example of how you are going to do this. How we are pushing the capabilities of cutting edge technologies. You are definitely new computing frameworks. At IBM, we were have setting the place in quantum computing for about a decade and progress is accelerating, right? We are advancing our processors. We are innovating in how we can handle and correct errors. We are bringing these systems to other forms of computing, and we are developing algorithms to unlock the value of heterogeneous computing approaches using quantum system. And now quantum computing is quickly approaching a very important inflection. So tell us about this, please welcome our VP Quantum Computing at our system, Jay. Come on here, Jay. Thank you.
Thanks, Sarah. So I get to talk to you about quantum. At IBM, we are actually been a leader in quantum research for over 40 years. But in last 10 years, some pretty exciting thing happened. That we were the first to put a quantum computers on the cloud in 2016. 1 year later, we were the first to create open source software development kit for programming computing, which we call KISS-Kit. And in that same year, we created the IBM network. This is community of academic enterprises, national labs, and or working towards the goal of discovering new algorithm or use cases for use quantum. Since the first quantum computer, we are actually developed over 80 quantum computers. We have over 600 users using quantum computing, and we have grown the quantum network to over 75 members. And all the learning and material, we have reached touched the over 10 million students. But things are actually going faster, and so I want to look back in 2022. We had a huge result. We actually broke the barrier of 100 students. We did the. I want to give some context. Imagine you had to represent qubit by bits and I gave you 10 qubits. 10 qubits, it's only a few kilobytes to represent this. So we go forward and imagine I had 30 qubits and you had to represent it. That's equivalent to a laptop. At 49 qubits to represent it is actually equivalent to some of the biggest supercomputers actually built. At 100 qubits, we would need to build supercomputers of 10 trillion times bigger than that ones built today to be able to represent 100 qubits. And with all the innovation we have done, we are actually at a 156 qubits now with our Heron procedure. And so you can see the goal of every even trying to realize even a 10 trillion times bigger supercompute today it's just impractical. So that we have done that allowed to get there. Why we can innovate so fast? This is the first we are actually very good at IBM semiconductors. I would say we are the only team approaching quantum computing as an engineering problem, not a research problem. To give some context, we have actually make a new device every 17 days. Every 17 days we come up with a new idea, we test it, and this allows to keep that cycle of learning, keep that innovation and push us to next step. And that's what we did in 2023. We wanted to get a point we called utility. And what that is that when a quantum computer is actually able to execute accurately quantum computation that are beyond what we can do with a brute force classical computers. The keyword of here, actually, if I had a computers and I couldn't trust the output, or it just a gave noise, it's not actually useful. At IBM, we are not interested in running random circuits. We want to make sure that we can accurate result and that we exactly what was recognized by team. Working with our colleague and workerly, we were able to first time to run an accurate result on a quantum computers at a scale beyond that you can simulate the classical computing. I will give the some context. I know this plot has a lot of information, but if you go back, we are actually the 100th year of quantum mechanics. And the art of making progress of those 100 years is actually coming up with a ways of approximating. And so what's shown on this plot is the result run on the IBM quantum Eagle procedure. and various approximate the solution I want to take two keys point from this. The first of all, these approximate methods are actually different. None of them agree. And the second is the ground truth. The reality is the one of run on quantum computers. So this is huge. We are the point where now running a quantum computer is better than using a classic computer. To simulate a quantum computer, so I have told you that we got to a point where it is impossible to represent on a quantum computer. Got to a point where it's better to run a quantum computer that simulate a quantum computer. But for all of you out there, you want to know when it is better to run a problem on a quantum computer than compared to running into a classical computer. That's when quantum is finally giving you what we in the field call quantum advice, where it's actually cheaper or faster. So I have told you we have got to a point where it is impossible to represent on a quantum computer, got to a point where it is better to run a quantum computer than a simulate a quantum computer. But for all of you out there, you want to know when it is better to run a problem on a quantum computer than compared to it's running into a classical computer. That's when quantum is finally giving you what we in the field call a quantum advantage, where it's actually cheaper or faster or more cost efficient to use quantum computers over a classical computers.
So originally, we rethought about this, and it's not quantum versus classical. It's actually quantum plus classical versus classical. And if I can get a cheaper, better result, then that's a win. And so in 2024, we came up with this idea we call quantum-centric supercomputing. And that's just exactly what it is. It's a hybrid computing architecture that leverages both classical and quantum computing. So now we can start to consider some real problems that this is work we have done with our partner in Recon, and it's like the simulator ground of the chemistry problem. And so you want to find the lowest energy of this problem. And so there are methods that exist classically that is either computationally easy to run, and there are ones that are really difficult to run. And they give you pretty good results. And what we are able to do is come up with this algorithm where we can run parts of the problem. No, one of our quantum processes, and that the rest of the problem is actually run on Fugaku, one of the world's biggest supercomputers. And that is actually amazing is that 45 qubit example of this iron sulfur cluster. We are getting results consistent with the best classical method. So now I'm comparing a quantum computer running it as a quantum computer to a classical computer running it as a classical computer. And we are getting results that are about the same. So now we want to go beyond this. We want to go bigger. And so we had to reinvent how we did this architecture. So in that first example, the team actually ran it on a quantum computer and then emailed it to the team in Fugaku in Japan. And then they load it up and run it on a classical computer. Obviously, that's not practical. So we have to go to a new regime where we have results that we have to accelerators. We either have a Fugaku, a supercomputer, as well as a quantum computer. And now we want to come up with a way of orchestrating being able to run to both of these. And unlike just having one accelerator, both of these are very expensive. So in this example, as we go through, you can see that the users submit their program and we have to create an object we call workflow manager. That's I left an ideal time on a supercomputer. I'm wasting resources any ideal time on a quantum computer. I'm wasting resources, so this is real. Orchestrating difficulties, problems. If we zoom on the quantum circuit that we find here in quantum circuit, runs it, goes to one of the Heron's processor, the processors comes it into turns into a random one or zeros, and we send it over to the supercomputer where take the result of the quantum computer plus an extra classical script, run a bigger problem that gives us a new set of parameters to repeat and run this multiple times. And then we have to iterate backwards and forward running between the classical and quantum computer, having them all idealized. So what I'm excited by is only a week old. We were able to go to 77 qubit system, and now look at us bigger molecule and actually start to see that we are getting comparable result. We are not getting exactly beyond, and at this size we even believe as a community that the lowest energy here may not actually be the real. So as we go forward, we would be able to get to a point where we are actually getting to what we call quantum advantage. For that reason, we are making bold statements because we are making progress in our hardware as well as the algorithm that are getting done, that we believe quantum advantage will actually happen by 2026. Thank you. And it's not just us, it's a community of researchers. Every month, every weeks, new papers get put out in different examples. I gave you a chemistry problem, but we are seeing examples in optimizing materials and so on. And so for this reason, I do believe we are going to see quantum advantage in chemistry first. Second, followed closely is an example and optimization. And then thirdly, there's a lot of exciting work in mathematical problems where the team and are exploring AI, quantum machine learning problems that could even have an impact in the AI in the future.
Future of quantum computing is the topic of our video, which is based on IBM Think conference.
We choose this topic because it represents the future of technology and innovation.
CEO we choose is Nikesh Arora, CEO of Palo Alto Networks.
We choose him because he is a visionary leader driving technological innovation and cybersecurity advancements.
The experience has been exciting and educational till now, giving us these insights about emerging technologies.
The main difficulties we faced were coordinating team schedules, and as our team members belongs from different regions, there were language
The
barriers.
video should help us to improve our creativity, communication skills, and presentation skills beyond academics.
The most enjoyable part was filming and editing the video together as a team.
I learned team spirits, patience, and time management from my teammates.
I learned research, speaking, and creative thinking during the video making process.
This project improve our teamwork and collaboration by encouraging open discussion and idea sharing.
My personal role was scripting and coordination, through which I learned leadership and team management skills.